This is video 6.2. It looks at the uses and hazards of radioactive emissions. Now, firstly, on the left-hand side here, we have the idea of energy production. And there are two key forms. There's fission, which is currently viable and provides a lot of energy throughout the world. And there's fusion, which is at the research stage. Medical uses, there are two key ones here. First of all, it's used to diagnose cancer or other diseases. So a tracer is about pinpointing, finding where a problem is. Radiotherapy, a therapy is a treatment, and radio meaning radioactive. Over on this side, we again have got the concept of half-life, so how active or how quick the decay is, and that's relevant to uses, as we'll see. And then there's the difference between irradiation and contamination. Once again, the key idea here, of course, is radiation transfers energy, and that energy can do harm or it can do good. So firstly then, the difference between irradiation and contamination. So here we've got something being irradiated. So it's used to kill bacteria in fruit, and this is exactly like shining light on something. Once you switch the light off and it's dark, it's gone, and it doesn't linger in any meaningful way. So over here, it's just as if it never happened, apart from, you hope, the bacteria are dead. Contamination, by contrast, is dangerous because here the substance is actually transferred. So whether it's dust or gas or a liquid, it's physically transferred to the object. So any time later, that object remains dangerous because it actually has the material on it. So half-lives, we've got pros and cons here. So a short half-life might be days or even minutes. A long half-life can be thousands of years or even millions of years. Now, if you're dealing with the same amount, say a kilogram, if you've got a short half-life, well, the upside is it's gone pretty quickly. After 10 days, it's almost all gone. But in order to achieve that high rate of decay, it must have a very high amount of radioactivity coming out of it. So as long as you contain it, and you contain it safely for those days, it's on balance probably a more desirable state of affairs. In contrast, if you have a long half-life, per second it's not particularly dangerous, but you need to look after it and keep it somewhere safe for potentially thousands of years. So somewhere in the middle is kind of the worst of both worlds. So there we have it. Half-life is a way of describing how dangerous something is. Then we have medical uses. Now, we saw this in the video on EM waves, but it's relevant here because gamma is, of course, a nuclear radiation as well as being an EM radiation. So we have the same animation here. We inject a substance. That substance is specifically designed to attach to where you suspect the problem might be, or the type of tissue. It bonds there, and as it concentrates there, you get the gamma being given off. A gamma camera, it moves all the way around, and it produces images like this, which allow us to see not just the structure, but the function, what's going on biochemically. Radiotherapy over here. So here we have a beam of gamma, and it's going to destroy this tumor that we can't get to using surgery and other means. Now, it rotates to minimize the damage to the healthy cells. If it didn't rotate, the healthy cells here, let's say, and here would get just the same dose. This way, the tumor is constantly being hit, but the healthy cells get only a minimal dose. So here we have fission. So this is energy production, and this is currently used in thousands of reactors around the world. So a reactor is essentially fuel rods, and they're a few centimeters in diameter, and they contain uranium typically. Now, these control rods move up and down, and they absorb neutrons, and neutrons are key. They are the ones that start the splitting of these atoms. But by moving this up and down, we control this reaction. So let's have a look at this. It's a chain reaction, although really a web reaction would be better. But the idea of a chain is one link. If you pull on a chain, one link pulls another and another and another, and so on. So this sequential nature is what they're after here. So our little film keeps running here, but in essence, we've got a neutron smashes into a large nucleus here. It splits it in half, and that releases energy, but also it sends off more neutrons, which in turn cause other nuclei to split, hence the chain reaction. So very, very quickly we get this rapid release of energy, and it's extremely powerful. It's about 1,000,000 times more powerful per gram compared to fossil fuels. And finally we have fusion, which is the opposite of fission, in that we're bringing protons and neutrons together. So it sounds a bit paradoxical, but this can also release energy. In fact, it's what powers the sun and all stars. Now we currently have this in experimental phase on Earth, but at the moment it's taking in more energy than it gives out. But the hope is that eventually it will provide clean and relatively clean and limitless energy.